Hey, PSTAT students, Mr. Mitchell here. We're going to continue to take a look at hypothesis testing. Today, we're going to really focus on the different types of errors that could be made. We're not talking about human error like 1 + 1 is 7 or something like that. That's just human error that we don't account for in probability. What we're really talking about are, if we think of medical type stuff, we're dealing with coronavirus right now. We're talking about dealing with a positive and negative tests. All right, false positives and false negative tests. All right, you take a test to see if you have the coronavirus, you get a positive or negative back. There's a chance that it could be a false positive or a false negative. So we want to take a look at that in terms of statistically what that really means. Okay, so we're going to talk about power and errors. Power is a good thing, errors are not. All right, we want to try to minimize the errors, but some of it just comes along with statistics. There's not much you can do about it. You can't have everything be 100% perfect. It's just not possible. Okay. So here's what we're trying to accomplish. Have an understanding of type 1 and type 2 errors and how they relate to each other. All right. What are the consequences of those decisions that we make from inference procedures? All right. Have an understanding of how power and its relationship to type 1 and type 2 error, how do they interact with each other? And then how to influence power. All right, and what are the consequences of the influence? All right, be able to calculate the probabilities of each setting. All right, so some probability calculations are much easier than others. So we're going to focus on both of them. All right, so some of the mistakes that we can make. If we reject the null when the null is true, this is type 1, and we label that as alpha. All right, so we've used alpha when we are comparing it to a p-value in our interpretation. We haven't really focused on what alpha represents. We've just been told to use 0.05 if they don't give you a number, or use 0.01. If they give you a specific number, we would use that. But that is the type 1 error. That is if you reject the null, but the null is in fact true. All right. And then type 2 is when we fail to reject the null, when the null is in fact false. So you should have rejected the null. This is type 2 error. All right, we label that as beta, capital B looking Greek letter, okay? Probability of committing type 2 error, we call it beta. Type 1 error is alpha. All right, so instead of writing out type 1 error probability, type 2 error probability, we've given them symbols. So then we don't have to continue to do that. We don't want to write anything more than we have to, okay? All right, so we've seen this little matrix before. It's a way to organize things. So we're not just writing it out. It's kind of an organized framework of what you should do. Okay. So if the null is true and you reject the null, that's type 1. Shouldn't have done that. The null was true. You should have stayed there. Okay. The null is false and you reject the null. That's the correct decision. Good job. All right. So the null is false and you rejected it. If the null is true and you fail to reject, that's another correct decision. All right. So, I mean, these are the good boxes that you want to be in, but there's no guarantee that you'll be there. Type 2 error is when you fail to reject the null, but the null is false. You should have rejected it and you didn't. And again, that's not you interpreting it incorrectly. That's a completely different thing. Like if you interpret the p-value wrong, that doesn't go on this matrix here. That's not what we're talking about. Okay. We're talking about the actual test giving us the wrong answer, basically. Okay, it's kind of the way to think of it, but the test didn't do necessarily anything wrong. It's the way the test is set up. Okay, so what we call power is this box here. It's a correct decision. It's when the null is false and you've rejected that. We call that power. All right, this doesn't have a special answer. The null is true and you fail to reject it. That's just kind of the status quo, if you will. If you want to think of it that way. That's why it doesn't necessarily have a name, because we say that it's true. It's really temporarily true, possibly. Okay, because we might run another sample later and prove that it is false. The way I think of it, if you've ever had a test that has questions always, sometimes, or never. Always and never are very strong things. If you can show that something happens one time, it's not never. And if you can show that it's something doesn't happen one time, then it's not always. It's a lot easier to say sometimes because all you have to do is show one time each direction, and then it's going to be sometimes. Even if it's most of the time, it's still sometimes. Okay. So again, we don't have a name for this. All right. It's just doesn't have a name. Okay. So here we go with some of these pictures I think are very helpful to try to understand what's going on. So this graph is the null hypothesis. This is what used to be true. This is the null. This is the old data that you have. Okay. And this is the new data that you have. This is the new sample. This is our sample mean. This is our population mean, if you want to think of it that way. Okay. And this is making us believe that this is not true. Okay. So there's an alpha. There's this line here that divides it. Okay. And that's where the critical region happens. So that's where, if you did a z-test, that's where the z statistic, the test statistic, that's that number, and anything further away, we call that statistically significant. Okay. The p-value, you would reject it if it were smaller than the alpha value that's here. And that's why alpha is pointing right here. So typically for a lot of times we use the alpha of 0.05. Again, there can be other alpha values, but that's typically what we use. So that's the type 1 error. That's the probability, the 0.05, that you're in this tail here. Again, it doesn't have to be 0.05, but when in doubt, we do use that number as a basis. Okay. So that's this probability here. So anything in this region is significant, means you reject the null. Okay. But that's also could be the error that you're making. All right. Even though that's the defined region of where we start to reject the null and go with the alternative hypothesis because of evidence that we have. But that's also where a mistake could be made, that maybe you shouldn't have done that. Okay. And then beta is that same critical value where that happens. Okay. That critical value where that occurs. And anything on this graph this way, that's type 2 error. Okay, so again, the boundary is really the same place. Okay, and that's, we call this, notice beta can go all the way over to here, and you might say, well, that's almost, well, that's the type 2 error that you rejected in the null. Okay, so we just need to understand the difference between alpha and beta and kind of understand how those two graphs kind of interact with each other. Okay, here's another different look at it here. We talk about it as, here's the p-value. Again, the p-value going this way, we say that that's significant. Over here, it's not. Okay, so the type 1 error is not on this graph. So green is true. This is the null hypothesis. And right here, anything to the left of that critical value, that's where the type 2 error occurs. And notice the closer you get to here, the less the type 2 error happens. Okay, so that's kind of the idea, the concept. If we just take out the alpha here for a second and just focus on beta, this is type 2 error. All right, so this was known to be true. This is making you question it. And then this is what can happen. This is where the type 2 error has occurred. Okay. Okay, just one other thing. Just want to make sure that we kind of clarify we're good on this. Again, what is type 2 error? It's when you fail to reject the null, but you should have. So you stay, if you want to think of it this way, you stayed in the gray and you should have went in the green. And that's the red. That's really where the red happens. Okay. That's kind of that concept. All right, so here's some other ways of looking at it. The powers, the probability that a significance test will correctly reject a false null. Doing the right thing, okay? Power is 1 minus beta. So if I go back to this graph here, whatever this red is, if I want to figure out the power, I take 1 minus that. Okay, so it's really the green over here is the power, okay? Again, this is true. We made the correct decision by going over here. So we don't have this. So that's the power of the test. All right. So increasing sample size n decreases type 2 errors and consequently increases the power of the test. So if you can increase sample size, that's great. All right. You need to redo the whole sample from what you maybe, you can't just go out and sample more people and add it to your current thing. You got to go start over and resample everything. So that does take time and money. All right. You would like to increase power. Increasing alpha increases the power of the test. So increasing alpha. So if you think about it, if we slide this way, or if I go back to this one, if I slide alpha this way, so from 0.05, we make it 0.1, or from 0.05, we make it 0.06. We make it a little bit bigger. That's going to make beta smaller, and it's going to make our power bigger. Okay, so it's kind of an inverse relationship, if you will. So increasing alpha increases the power. Increasing alpha decreases beta. You can't, thinking of coronavirus, you can't have a decrease in false positives and false negatives at the same time. You can decrease one, but it's going to increase the other. So it's an inverse relationship that way. Okay, you can't decrease the both. It would be nice if we could just say nobody's ever going to have a false positive or a false negative to say whether you have the coronavirus or not. But it's going to happen. All right, it's unfortunate, but there's not much we can do with statistics and science to make it foolproof. All right, so you have to decide which is worse, and you want to try to limit which is worse. You'll deal with the one that's not as bad. Okay, and a lot of times in our class, that's what we're asked to do. We're asked to say what is type 1 in this situation, what is type 2 in this situation, and then say which is worse, and then we'll adjust and make that the lesser of the two evils, if you will. Okay, with the coronavirus, thinking of false positives and false negatives, a false negative is worse, and usually type 2 error is, usually, not all the time, especially in a medical situation, because you're told that you're healthy. False negative means you didn't test positive for it. False negative means you have the virus, but you tested negative. It means you don't think you have it, but you do. What does that mean? That means you could infect other people. Okay. A false positive means you're told that you have the coronavirus, but you actually don't. That's type 1. So you're going to quarantine, but you don't actually have it. So you're not sick. The worst part of that is you'd have to quarantine. So you might not be able to go to school or work, but you wouldn't be, there's nothing else. That's the negative side of that. Okay. So another thing, increasing the difference between P naught and P sub A will increase the power. Whether we're talking about a mean or a proportion, that we're dealing with it in a proportion sense here. We could also talk about it as a mean. If I come back to this, if I change the mean here and the mean here, if we slide those further apart, you can also increase the power. If they're closer together, well, then it's easier for them to overlap. And then beta is not as strong. Okay, if these two peaks come closer together, all right, then there's more overlap for this red here to occur. All right, so the further you can get those apart, all right, the better. So larger difference between mu sub naught and mu sub A. Again, we're dealing with it back in terms of means. It's either proportions or means, right? We have to be able to deal with both. So mu sub naught is the null, the original mean, all right, your population mean. And then this is your sample mean, if you will, okay? So you can see the further apart they get, the power increases. So when they get closer together, the power is decreasing, all right? So you can see this is alpha. This blue region is alpha. But you can see, look at the red shrinking. Look at the red over this light red. See the light red increasing and decreasing? That is your type 2 error increasing and your power is decreasing. So now, okay, now the light red's disappearing, the dark red is increasing, that's your power. So the further apart those get, and that makes sense. If you had something that was true, or it used to be, and now this number in the new sample is completely different, it's going to be easier to make the decision that this wasn't true. When they're closer together, this may be true, but they're not so far apart that it even makes that big of a difference. Okay, so the null may not be true anymore, but how big of a difference is it? And is the null really different? Is the new mean different from the old one? Okay, so that's the one way you can change it. Another way is increasing alpha. Okay, so right now, the blue is alpha. And notice alpha is decreasing. Oops, sorry about that. Clicked too much. So notice alpha, the dark blue is decreasing almost to nothing. And now alpha is increasing. So the dark blue is increasing. The light red is decreasing. That means beta, or type 2 error, is decreasing. And notice my power, as alpha increases, the power, as alpha decreases, the power decreases. As alpha increases, the power increases. But type 2 is shrinking right now. Beta is getting smaller. Beta is getting smaller, smaller, smaller. Power is increasing. Power is increasing. Okay, now beta is growing and power is decreasing. So if you're concerned about type 2 error, you'll get a larger alpha value. Okay, so then your power will be larger. Okay. If type 1 error is your major concern, then you make alpha really, really small if you're not worried about type 2 error. Okay, so it just depends on the situation. It's possible that type 1 is worse than type 2. I don't think with medical testing that it usually is. Okay, usually type 2 is worse. So this is another way, the second way. So another way is to increase the sample size. Now, remember, when you increase sample size, you decrease variability, meaning the spreads will shrink. So as n increases here, notice they're starting to shrink. We're going to 100 and then back down. So as the sample size decreases, notice the variability starts to creep further and further away. All right, and that's kind of the idea of the central limit theorem, okay? And sampling distributions and all that stuff kind of coming together here right now. As n decreases, notice there's more and more overlap. And when there's more and more overlap, notice your beta changes. And when beta changes, then power changes because they add up to 1. Your type 2 error and power add to 1. Okay, so as n increases, the power is going to increase, beta is going to decrease. Okay, and notice this is the type 1 error. We're trying to keep that the same because you can keep alpha the same and not change the sample size. Okay, so notice it looks like the type 1 error is not changing here. Okay, so we're trying to change the type 2 error by increasing the sample size. So that's one of the optimal ways to change things, but also sometimes you can't do that. You can't just go sample a few more people. You have to sample everybody randomly. Okay, so that's another way to do that. All right, so let's go through one problem together, and then I'll turn you loose here. Okay, so stage 2 hypertension is defined as a mean systolic blood pressure of 140. Individuals with stage 2 hypertension are at a severe risk for heart disease and stroke. Pharmaceutical company is testing an experimental drug, Bethanol, in an effort to reduce systolic blood pressure in individuals with stage 2 hypertension. 36 randomly selected volunteers with stage 2 hypertension took Bethanol for a 6-month period. As the group, the volunteers had a mean systolic blood pressure of 134 and a standard deviation of 12. Many volunteers experienced some adverse side effects. Do these data support the pharmaceutical company's efforts? Okay. What would be the parameter and hypotheses of this inference test? So we have a sample mean and standard deviation. Okay. We have a population mean. All right. So the parameter is the true mean systolic blood pressure of individuals with stage 2 hypertension. All right, so there's my parameter. And here's my null and alternative hypothesis. Remember the null, we need to have the true mean in here. All right, on some other past activities, some of you are getting your sample mean in here. Don't do that. No, it's always the parameter. That's why we're identifying the parameter immediately, okay? Parameter population. So the null is always dull, there's no change, and we're trying to lower the blood pressure. All right, we're not trying to change it or make it greater. When I say change it, that could be a not equal to, that would be both tails. All right, so that's our step 1 process. All right, so construct the sampling distribution of the null hypothesis, justify the characteristics. So basically, we're just finding the mean and the standard deviation. in the shape. So the mean is 140. That's the distribution of the null hypothesis. The standard deviation was 2. All right. And then the shape is approximately normal. Okay. And so where did the mean is the mean? Okay. The standard, the standard deviation is the sample standard deviation divided by the square root of n. Okay. So the square root of n is 36. I'm sorry, the sample size is 36. The square root of 36 is 6. So 12 divided by 6 is 2. And then since we're greater than 30, we are approximately normal. All right, we still got to think about the central limit theorem, large counts. And we are, because of the 36, we are approximately normal. We're not told normal, we're approximately normal. Okay. Soon we use a 0.05 significance level. Mark that on the above sampling distribution and find the corresponding sample value. What does this value represent? So we're really finding where that critical value happens. Okay. You don't have a handout, so that's why you don't have anywhere to mark it. Okay. But we're trying to find where that critical value happens. And you can do inverse T. If it were a Z, if we had the standard deviation of the population, you could do inverse norm. But inverse T operates the same way. Okay, you're trying to find that critical boundary of where that starts to happen. And that occurs at negative 1.68957. Okay. So that's the critical value. You're trying to find where that occurs at. Okay. So things start to become special, if you will. I say special, that's not really a technical term, but they start to become special at 136.62. All right, basically what you're doing is you're backwards subbing in the formula to find this value. Okay, here's your inverse T. This is the T statistic that you would use. That's where things become critical. All right. So what does this mean? It means we're going to reject the null hypothesis. Our sample mean, again, we're not comparing p-values. This is another way that we can compare things. This number is further away than this number. So you're going to reject the null hypothesis. Okay. If we look up probabilities and find our p-value, we'll find that the p-value is smaller than the alpha value. Okay. All right. The alpha value is 0.05. If we went through and calculated our test statistic for 134, we're going to find the p-value is smaller than that. Okay. So that's kind of what we're going to do next. All right. I know we haven't done a whole lot with this, but there's two different ways to look at it. You can look at it as the test statistic being further away, or you can look at it as a p-value being smaller. And either way works. So we got to find our p-value. So we would use our formula to do that. All right. So T equals 134 minus 140 over 12 over the square root of 36. That's where this number came from. And then you would look that number up either in the table or with the formula. Again, I know a lot of us just use the different tests on the calculator. That is fine. You would get this number from that. Okay. And you would get this number from that as well. All right. So recognizing that our sample mean is not static and could change due to sampling variability, describe in context what the 4 outcomes for the conclusion of this inference procedure and what are the consequences. So what are the 4 things that can happen? Well, 2 of them are correct decisions, 2 of them are not correct. So we could reject the null when the null is true. We could reject the null when the null is false. We could fail to reject the null when the null is true. We could fail to reject the null when the null is false. Those are the 4 things that could happen. You reject when it's true. You reject when it's false. You fail to reject when it's true. You fail to reject when it's false. So those are the 4 things that could happen. Okay. So I'm thinking about our consequences. So reject the null and the null is false. So this is a good decision. We fail to reject when the null is true. That's a good decision. We fail to reject when the null is false. That's type 2, and there's type 1. Okay. Right. There's our decision matrix. Okay, so based on what we just talked about, decision matrix, comparing the two. All right. We're not going to do that on a number line. So reject the null when the null is true. That's type 1. That's alpha. It's an incorrect decision. Reject the null when the null is false. That's power. We find that y1 minus beta. And then we fail to reject the null when the null is true. That's 1 minus alpha. And then we fail to reject the null when the null is false. That's type 2 error, which is beta. Okay, so those are the decisions that we can make. All right, find the probabilities of the 4 outcomes. Ooh, now some of the stuff we've done before, some of it we haven't. So type 1, alpha, power, 1 minus alpha, and type 2 is equal to beta. So this was given to us. All right, well, that's 1 minus. But then these two, you don't know how to do those yet. You're going to right now. And it really is just finding a z-score, a test statistic. You just have to know what numbers to plug in and where. Okay, it's not anything excruciatingly difficult. You just can't get confused on certain things. Okay, so again, we're dealing with this problem here. Okay, so our true mean, at least our null mean, maybe it's going to be changed later, is 140. Our sample mean is 134. So we're using alpha of 0.05, right? That was given to us. So we're going to do inverse t of 0.05. What's 35? Well, that's the degrees of freedom. Remember, when we do t, we need to know the degrees of freedom. If we pull up our calculator and do inverse t, we're trying to find that critical value of where things become special, okay? Not necessarily the p-value, even though that's where it happens. We're finding the actual value that when that occurs. So t star is really what we're looking for. So that's at negative 1.69. Again, you can use the calculator. You could use the table to do that. Most of you would use the calculator to find this. So inverse t is the same as inverse norm. If this were a z-test, then we would be using inverse norm instead of inverse t. Okay, so there's your formula. We've looked at this formula before, and that's the formula we're going to use. Okay, x bar minus mu over s over the square root of n. So this, we don't know the sample of where that occurs. Like, what is the average number? Like, we know this is the average that a sample came from, but we don't know the average number that makes it special, not special. Like, where is that dividing line of a sample mean? What would it be? Okay, we know the t star of where that happens. We just looked that up, but we don't know x bar. So that's what we're finding. Here's your sample standard deviation. There's your sample size. There's your population mean. So you go through and you calculate that. That's the 136.62. That's our x bar. All right. That we found where things, the sample mean, if you got a sample mean anything smaller than that, then you should reject the null. Okay. If you get anything larger than that, you should fail to reject the null. That's kind of your dividing line, if you will. So right there, there's your dividing line. All right. Special's over here, not special. Okay. So now to find the power, you're finding the probability that you're further away than this. I'm sorry, you're finding the probability that, that you're further away than that. Okay. That you've made the right decision by coming over here. All right. So TCDF, again, I know we haven't really practiced that a lot. TCDF is the same as normal CDF. You have a lower bound, you have an upper bound. Okay. And then you have degrees of freedom. It's really the same concept, okay? And you get 0.901, okay? So that's the power. If you're going to do it by hand, if you're going to do it by hand, you take this number, plug that in here, subtract, you get this, and then you do power. Sorry, my slides were out of order. I apologize for that. So you take your sample mean, plug it in here, and get your test statistic for this. All right, your sample mean minus your sample mean that's critical minus your sample mean that you actually got, and find that value. And then anything below that, that is your power. Okay. It's a lot. Okay. But it's really just two test statistics. Okay. And you've done that many, many times before. Okay. You've done z-scores over and over again. So just to recap, we're going to find our X bar that makes things special. Okay. We find our critical value, then we find our X bar that happened at the same place. Then we find our test statistic that comes from our special boundary mean and our sample mean. Notice the standard deviation and the sample size have not changed from here to here. Okay. So then what's beta? What's type 2? Well, that would be 1 minus this. You would just take 1 minus that, and then that's your beta. Okay. So this is the first year where they've actually, last year was supposed to be the first year they said that they were going to make you calculate power and beta by hand. They've never really had you do that before. Are they going to do it this year? I would bet that they're going to do something, but they may hold off until we're under better conditions. But I'm not saying that they won't have you do that. What I am telling you, you do need to understand the different kinds of errors, how they are interpreted, and what their negatives are, what the repercussions are of having type 1 versus type 2. All right. So let me know if you have any questions.